To keep a quantum system stable, engineers typically place it inside a dilution refrigerator, a massive, multi-tiered tower of gold and copper circuitry designed to block out the surrounding environment. They do this to create what physicists call a good cavity environment. In these highly reflective, tightly sealed spaces, everything must be chilled to near absolute zero to ensure thermal noise doesn't overwhelm the delicate harmony of the quantum state. Relying on these extreme temperatures makes generating and maintaining coherent quantum states, like Bose-Einstein condensates, incredibly expensive and fragile. The sheer physical size and energy demands of these cooling systems severely restrict where optical quantum computing can actually be deployed, confining the technology to highly controlled laboratories. Curious, which raises a practical question. Is it physically possible to achieve that exact same phase-locked quantum synchronization in a lossy, high-noise, room-temperature environment? This paper, published by researchers at the University of Cambridge and UC San Diego, proves that it is. The research team utilized the bad cavity limit, building a deliberately leaky optical system from self-assembling gold nanoparticles. This approach allows collective phase order to emerge from a high-loss environment, using the dissipation itself to drive the emitters into synchronization. This scanning electron microscope image reveals the foundational structure, a tightly packed 2D array of gold nanoparticles, each 80 nanometers wide. Looking at the schematic, we see the critical feature. The space separating these metal facets is extraordinarily small, measuring just 0.9 nanometers across. Inside these sub-nanometer gaps, researchers positioned the active component, organic dye molecules known as methylene blue. Together, this structure forms what is called a plasmonic nanocavity. Because the physical space is so intensely confined, the tiny gap acts as an extreme amplifier for electromagnetic fields. Under normal circumstances, hitting a random collection of these dye molecules with a laser results in chaotic, entirely uncoordinated light scattering. The specific geometry of the nanocavity forces these molecules to align their dipoles with the intense optical field, enabling them to couple into a single collective mode. To test the system, the researchers fired a tightly focused, continuous wave laser directly into the center of the nanoparticle array. These emission maps compare low and high power. As power increases, an anomalous halo of synchronized light expands outward into untouched areas. The mechanism diagram shows why. Molecules rapidly share their optical phase, hopping energy outward through plasmonic modes. These spatial coherence heat maps track that specific relationship. The data confirms that phase locking holds tightly across the physical space, maintaining structural order even as the signal experiences rapid temporal decay. The emergence of this structured, coherent halo proves that the previously random molecules are now operating entirely as a single macroscopic quantum state. Physicists classify this newly observed behavior as driven-dissipative synchronization. The order we see arises precisely from the balance between the continuous pump power going in and the rapid light leakage escaping out. Because these structures literally self-assemble at room temperature, engineers can bypass the multi-million-dollar microfabrication facilities usually required to build quantum hardware. This scalable method opens a direct pathway for manufacturing ultra-fast optical computing components, ambient sensors, and practical molecular readout devices. Establishing quantum optical behavior at ambient temperatures removes the final physical barrier to integrating these photonic circuits into standard, uncooled electronics. If you want to see more breakdowns of recent scientific breakthroughs, hit the like button, subscribe to the channel, and let us know what topic we should cover next in the comments below. Today's episode was brought to you by Synestech Systems LLC, founded by Shane Persinger. Thanks so much for watching, and we'll see you in the next one.